everyone. Welcome to Circuit by Net. We in CAS host these events almost every once a month. So the first event, these events, we bring the technology to everyone, in the value, what's going on with the world, and also we have new technology trends or summary of this working on. So it's a very, I would say, very informative and thought-provoking process. So we welcome everyone to join our events. And if you are a IEEE member or CAS member, it's great to have you here. And meanwhile, I encourage you to volunteer and become an officer. If you are not yet an IEEE member or CAS member, please support it for you now. And it's very beneficial. Two events like this. Today we have Dr. William Damian giving us an overview of signal integrity. So Dr. Damian is from Ethiopia originally, and he received his bachelor's and master's degrees from Columbia in electrical engineering and PhD in electrical engineering from UIUC. In the past, he worked at IBM, HP, Electric Technology. In 2000, he joined Rambus and was responsible for signal integrity of the multi-gigabit parallel serial interface. In 2017 and 2020, he joined Intel, was responsible for signal and power integrity analysis for high-performance PDA, including fabric and high-speed I/O. In 2020, he joined Meta as analog mixing architect in the Meta Reality Lab. Dr. Damian has published numerous IEEE publications in various disciplines, including packaging, interconnect modeling, interface design and analysis, as well as applications of machine learning and optimization techniques to signal and power integrity for complex systems. He is currently a senior area editor for electrical performance of the systems of IEEE transactional CP and the senior member of IEEE. He also served as a distinguished lecturer for IEEE EMCS and IEEE EPS. So without further ado, let's welcome Dr. Damian.
Thank you for the introduction, for kind introduction. And also thank you, the committee, for inviting me to give this talk. So, as was already described, I currently work for Meta platform. Today's talk is to give an overview of signal integrity. And since I am not sure about the background of the audience, I'll try to start on basics of signal integrity and quickly ramp up to the latest and fastest, high-speed link analysis. And I will leave for the chairman how to proceed in terms of question and answer, but I will be happy to answer any question you may have on my presentation. So let me first share my topics. I have 4 major topics. I'll first give an introduction and what signal integrity is, why we are so interested, especially in the design of high-performance system on signal integrity analysis. And then I will address the most critical part of signal integrity. Not that it is only a part, but I'll address the interconnect models, why we think that is critical element of signal integrity. And then I will add the transmitter and receiver, and I will give in the third section about high-speed links and address different types of increasing the performance of current electronic systems. And then to design successfully this type of system, we always need some simulation platform. And interestingly, it's a very critical topic in signal integrity as well. So I will address that in my last section. So if you just look around the electronics products, whether it is compute or memory systems or other systems, you will end up seeing chips and sensors communicating or exchanging data. And we want that data to be reliably transmitted and received. And these interconnects between chips and sensors and attenuators, they have different types of interconnect and how we can handle it, whether it is package trace or board trace, or in some cases, even cables. Why do we, first of all, use that type of interconnect? And then how do we model them? And then, obviously, signal integrity is critical because the performance and even including the power efficiency of an electronic system will depend on signal integrity. So let's look closer of any systems. I have shown you big systems earlier, but if you just take the basic components, there will be 2 or more chips if it is electronic systems. And it also includes power sources like PMIC or voltage regulators. And signal integrity is concerned, making sure that the chips or the sensors, multiple of them, reliably exchange informations. Okay, so in that sense, signal integrity is a subset of electromagnetic theory. Even though here we don't deal about magnetic field or electric field directly, we often deal about currents and voltages, but they are really can be decomposed into magnetic field and magnetic field and electric field. So so from that point of view, signal integrity is part of electromagnetic theory. And sorry. So we try to make sure that communication between chips are reliable. But one thing we don't have to forget is, yes, signal integrity is very important, but in the same topic, there are power integrity, EMI analysis, which really closely related topics. However, for these presentations, I will address only signal integrity. Nevertheless, I also acknowledge the importance of power integrity and other related fields. So I repeatedly said, that signal integrity determines the performance and even power of our electronic systems. Why is that? Because the whole idea is the more transistors we have in a chip, the more data we need to provide the chip to use it very effectively. Not only that, this data has to be communicated between multiple chips. And if you want to do that, there are only 2 ways to do it. Either we have to transmit data very fast, or we have to create many connections between silicons to make sure that we get big or large amount of data to transmit from one chip to another. So interestingly, both approaches have challenges. So if I just address increasing the data rate, obviously you will see the more high frequency content my data has, the more losses I will see. So that is easy to address. But often that is not appreciated until you really work as a signal integrity, is even to increase wire, the number of connections, and transmit in aggregate large amount of data has very big limitations. So to express that idea, I have a picture on the top right corner. The differences are in terms of scale. On the chip, you may have a very high or very small dimensions, so you can be able to have a large amount of connections. But eventually, if chip A need to be connected to chip B, those traces has to be connected to the package, which have coarser, rule of design. Not only that, it has to go through the board, which board doesn't allow you to have the same fine traces that you will find in a chip. So because of that, increasing the number of lines between two chips is not very easy to obtain. So both systems have a very important limitations. But nevertheless, if you look back at the current, the tendency which we have, for example, on the left side, I just plotted the memory speed. That means how fast the data is transmitting between memory and controller, memory and CPU. And you can see that since 1995, the data rate has been increasing or doubling every 2 to 4 years. So we need more memory because our phones are now much more capable of doing very interesting things compared to 10 years ago or even 4 years ago. So that's one side of the story. And then if you go on the right side, for example, the internet, how you download stuff from the internet or how you work with a data center is also getting faster. And that is captured on the curve on the right. So the data rate increases really determines the performance of our electronics systems. So let me show you some of the challenges we are facing to run very fast. Here I have two chips. One is, I consider it a transmitter, and the other one is a receiver. So if I try to transmit 001000, a single bit, and receive it at the receiver chip B, you will see very interesting phenomena. The blue pulse was the pulse that I send from chip A. But due to this interconnect, by the time it gets received by the output, at the chip B, you see very different pulse than what we send. And these differences can increase as we increase the data rate. And the output is much smaller, and even the shapes, and we see a lot of reflection. That really, bring our attention that the pulse is really heavily distorted. So a signal integrity is trying to fix or to find out a solution for this type of problem. Okay, so again, this distortion is a function of frequency, but also is a function of the interconnect. If the interconnect is long, or if it is not very good conductor, the distortion will be very different. So how do we measure that? In general, the way we characterize or understand the behavior of an interconnect is what we call it scattering parameter or S parameter or insertion loss. It's a little bit new terminology. If you are really limited in circuit design or digital design, you don't see these words. These are terminology or parameters that came from RF world. But it shows you the behavior of the interconnect as a function of frequency, even though here I only show you a delay, attenuation, but this S parameter represents the phase and the delay altogether. But one thing to consider is I have here 3 different channels, which really means I have 3 different interconnects, but you can hardly see the differences between them. The only good thing about the picture here is the data is limited between 0 and 1. We like that because that increases the dynamic range. We can really represent a parameter without worrying about error, amplifications or some other in undesirable phenomena. But the issue is when there is small differences, we can't really tell. So because of that, we a lot of time in signal integrity, we use dB scale. So these two pictures are identical data, but the one on the right is in dB scales. So by just drawing that, we can see which channel is better and which channel is not so better. So dB scale is very often used by us. And the reason is it kind of exaggerates or shows us, not really exaggerate, but truly show us which channel is better than which the other channel. So I just want you to be, if you have not heard this type of representation for a interconnect or circuit element, we do use it very often, and it comes from RF world and even other fields. So earlier I showed you how channel or how interconnect affect a single bit. If I just send a single bit, how does it distorted? But really, when you do communications, you send a stream of bits, as I showed you here. And the interconnect will do a very interesting thing to this behavior. Remember, interconnect has a delay, has a loss, and in some cases has a memory, because when you transmit something, it will take time before it showed up on the other side of the channel. So what you will see is here is, because of the channel imperfections, you will see this type of waveform. But eventually, the receiver designer has to recover or modify this received signal into what originally has been sent. So really, the signal integrity folks need to deal with this picture in the center. What does it mean? So the way I look at it is not very straightforward. So it's not very straightforward. So to minimize our challenges in terms of seeing how this channel is affected, we use a matrix known as I diagram. I diagram is very similar to error vector measure that you might find in radio frequency. It just represents the losses or the losses or the disturbance in your signals. So the way we do it is if you see on the top right side, you have these bit patterns. We actually cut them into pieces for every period or clock according to the clock speed or clock width, and then we superimpose them, and you can represent the picture right all the way on the right side or on the left side on the top by a picture which is easy to understand on the left side on the bottom. So this is called an I diagram. We use this a lot in signal integrity because it's a very compact way to show us the imperfection in the channel. And how do we decide? We just see the width in terms of horizontally, which is called timing margin, and the height in terms of vertically, which is called the voltage margin. Okay? So all this dispersion and go ahead. Yeah. So the question is, how do we define how much timing margin and voltage margin one need to have? And generally, if the design is a standard design, by that I mean if there is some body which controls the standard, they will define that. But if there is no standard, then it's something you design or your company design, which doesn't have standard, then it's up to the sensitivity of your receiver to define that. Say if you, let me just go back to answer this gentleman's question. If you have very sensitive receiver, then your voltage margin can be shrunk and you can be able to recover even very, very noisy systems. So yeah, again, timing wise, it's a little bit complicated, but it depends on the accuracy of your clock source or your CDR. I'll review this, some of it slightly when it comes up. So in general, in late 80s, I don't want to date myself, but during that time, nobody talks about impedance discontinuity, return current reflection. All the people who design, fortunately, I used to work for IBM when they designed mainframe. The only thing we worry about traces were delays. If we know the delay, that's enough. But you can see that at that time, most of the systems ran only 30, 20 megahertz or things like that. But since early 1990s, things start speeding up. So now we need to worry about not only inductance and capacitance, resistance and conductance. And I'm sure many of you, where you were in undergrad, when you build electronic system, when you wire on your prototype systems, you never worry about signal integrity. You just wire them, it works. Or at most, the only thing you need to worry was delays. But that is because the speed was not that high. But eventually, as the speed becomes increased, the non-idealities that becomes important is listed here. Okay, so we are really at right now, we worry about all these non-idealities when we deal with the signal integrity. So there is a lot of work to be done. So let me just take a break and review what are interconnects, because that's the main source. Remember, signal integrity is not about only interconnect, about the transmitter and receiver and the whole picture. But the dominant part or the challenging part is really the interconnect. So I here listed different common interconnect systems. For example, the one which is called microstrip is really a trace on a plane. And then in between, there is dielectrics that is based on the manufacturing things. That requires, based on the manufacturing material, what needs to adhere to the copper, if it is copper, or if it is alumina, what is the material that will be able to sandwich it. So it's all about process simplicity. And then in the second thing, I show a strip line. If we really worry about high speed, we want to sandwich the signal between planes. And then on the lower pictures, I try to show coaxial cables. But in general, the first choice is really what is easy to manufacture. That's the reason why PCB is become so a king for so many years. PCB was there before World War II, or maybe even before. So it is still here because the manufacturing technology is very straightforward and very inexpensive. Okay, so there are new techniques that try to improve it, but life is not as simple as I saw as the pictures I show you on the right columns. Sometimes we have to connect the board with a package, or sometimes we have to connect a board to board. So connectors and what I say here, BGA, ball grid array, will come into the picture. So it kind of make it even challenging for us to characterize this type of systems. It's not easy to, maybe sometimes there is no closed form solution, even if you understand Maxwell equation very well. It's not easy to come up with a representative for this type of structure. But in life, we have to deal with it. Fortunately, there are very, very capable tools, electromagnet tools that people make a lot of money and serve the wide industry. So we use a lot of electromagnetic tools to capture that. So I keep saying electromagnetic. What is the deal about electromagnetic and signal integrity? The reason is I show on top a signal. This signal can be a current or a voltage, depending on your transmitter and receiver. But eventually, it can be decomposed into electromagnetic waves, electromagnetic waves and electric waves. And it generally propagates, in Z direction. Then your solution will be easy. For example, on the picture on the bottom, microstrip, if you really want to transmit a signal, the waves looks like this. So that's the reason. Really, eventually, we have to represent these electromagnetic waves by some type of equation that our circuits or SPICE or some tool can understand. Okay. So the easy way is really, go ahead. Yeah. Yes, those are the tools. I have one slide about the tools. I will just ask your patience when I go there toward the end. So really, these electromagnetic waves are, in an instance, they are current or voltages. So we really love current and voltages. I assume many of you here are somehow related with circuits, even if you are doing digital. So we try to represent the interconnect with this type of things. How many inductance, how many resistance do you need to represent an interconnect? It's a matter of what is the data rate you want to model. But the good thing is these representations is repeatable, because if it is uniform, once you have a relationship for small section of it, you can cascade it very systematically. So for this type of structures, can I generate an equation that describes the relationship between the current and voltage? That's all it boils down. So I don't want to bore you with complicated equations, but the picture on the lower left is what I showed you earlier. If I just try to do circuit analysis, Kirchhoff law and KCL rule, I probably forgot how it is, but if you come up with a KCL and KVL rule and define the voltages, and then you represent the R and the L's with n infinitesimal elements, you will end up with the equation in the box on the right, which is partial differential equation. To be true, one is voltage and one is for current, but they are coupled. So the true name is coupled partial differential equation. You'll end up with that, and your circuit simulation have to give you the parameters. So the good thing is, I don't like equations. I want to make sense out of it. So if I combine those two equations from first order differential equation to second order differential equation and write it for the voltage only, you can see a very clear relationship between the model and the thing. So the first item is RG times V, which is really a DC term. And then the second term has RC and LG. It's a dispersive. You can't call it lossless, or you can't completely call it lossy. It's a combination. That is really the challenging part, which is the diffusion and propagation equation. And the right one, the LC component, is really a wave equation. All it says is the signal is delayed or goes through time. There is no loss. So the equation is very interesting. You can separate them. The good thing is, depending on what material you deal, the R may be dominant than L. So you can remove it. Okay? What do I mean by that? The reason is, if I just want to show you a typical number on the right, if I am dealing about chip, you can see that the resistance is much higher than the capacitance and inductance. So I can kind of ignore some of the L and C's parameter. I can just concentrate on the G. On the other hand, if I'm dealing with cables, in the cable, you can see that the cable inductance and capacitance are very huge, but the resistance is zero, almost zero. So I can ignore cable loss. I can just say how long is the cable is, and I will just multiply it by per unit length, and it's a delay. So we do this type of calculations if we are comfortable about our terms. But again, here I'm minimizing or simplifying things. And the way I simplify is R, L, C, G are constant number or constant matrices. But in fact, they are not constant matrices. So here I'm showing you, beside R, L, C, G, there is what we call skin effect. A skin effect is when a current passes through a copper, the current doesn't distribute across the copper uniformly. It tends to be limited to the edge, to the surface. Just this is again the result of electromagnetics. So even if you have big copper, it doesn't mean your copper all cross section is used. It depends on the frequency. The higher the frequency is, the current is only flows on the surface. So that actually brings to the resistance frequency dependency, which is actually a function of the square root of a function of f. And the same way, dielectric loss. The dielectric loss is also a function of frequency. That's why, depending on what type of microwave you have, it will heat up your food very fast, because the way it heats up the microwave heats up your chicken or any other tool, any other food, is using the dielectric loss. That dielectric loss is consuming energy. That's how it gets warm. So we use this phenomena for our advantage or disadvantages. So that's why I listed many high order terms. But eventually we have to design a system. So I showed a picture on the lower, again, left side. In actuality, we can't say the communication between chips are only based on strip line. Sometimes we have to bend, go through a via, So in actual design, it's a mix of different interconnect geometry. So that's what I represent on the picture on lower. And the whole thing is we can't put different interconnect close to each other, because then through the dielectrics or through the air, there will be a crosstalk or energy can be transferring. So one of our concern is when we design systems, we call it a crosstalk. That is really important in our field, because otherwise your board or your system will be very big. So you want to you want to design interconnect close to each other, but provided that the crosstalk is not beyond the limit. So here I'm just trying to show you why crosstalk is being generated and how to characterize that. So again, a lot of times we deal with judicious design techniques, but if it really becomes challenging, we can also come up with a slightly expensive method to minimize crosstalk. So far I'm assuming we are trying to communicate between chip 1 and chip 2 through a connector. So if I want to connect one chip to another, I just use one line. But I just told you, when we do that, we have to worry about crosstalk and then many other things. But I can also use two traces for communicating the same information. That actually is even less affected by crosstalk, because on one trace and the two closest traces, I send a signal that are out of phase. So anytime there is crosstalk, it will be canceling. So I try to represent that pictorially. If there is a crosstalk at the receiver, if it is differentially routed, the crosstalk will cancel and you will be out of you will be without crosstalk. What is the problem with this? Why don't we design everything like this? Because it takes 2 traces to represent 1 connection, so it is expensive. Okay, but sometimes we do that a lot. I quickly move to clock, because so far I have been talking about data, but when you communicate between 2 chips, there are data, but we also have to deal with the clock, because the clock tells the 2 chips how to synchronize, how to communicate at the same time. Otherwise, you cannot have the communication between two systems. So generally, there is what is called parallel link. So here I'm showing the red picture, or the one on the bottom is a clock. So for example, in memory, for every 8 or 16 traces of data, we send 1 clock. That syncs the clock between the transmitter and receiver. But the problem is we need 1 trace. So if that is very expensive, this may not be the right choice. So another one is where we don't have separate trace for clock, but the serial link, it's called serial link, where the clock is embedded in the data. So the receiver has to figure out what the good clock is. So that actually adds a lot of circuitry on the transmitter and the receiver side. But the good thing is you don't need separate clock nets. So there are advantages and disadvantages. For example, in mobile phones, between memory, we always use parallel link, because the 2 devices are close to each other. Having a clock from 1 chip to another is not very expensive. In the memory also, we do the same thing, because the memories are very close to each other. Within 8 inches, we do that. But in a very big systems like routers and servers, the transmitter and receivers are very far apart. So designing 1 trace just to transmit the clock is not reliable and also not economical. So in this case, we use embedded clocking, or what I mentioned, the second clocking mechanisms. So depending what type of interface you have, one is better than the other one. I'm not saying one is always better than the other one, but you have to evaluate the whole systems. Okay. So earlier I told you, hey, to remove crosstalk, you can use a differential, but the problem is it's two connections. Is there something in between? Yes, there is something in between. We call it multi-wire, or there is an example called CFI. Instead of using 2 or 4, we can use 3. You get the advantage of cross differential, and also the advantage of single. So it's in between. So there are standards. Even CFI is mainly used, for example, for mobile industry processor, for displays in your phone, or other virtual reality equipment. We use CFI or MIPI CFI for that purposes. So there are standards which take the compromise between differential and single-ended. So these are the things a signal integrity engineer need to analyze to evaluate the performance of the system. But we still want to run very fast. If you look at it, the third slide, I showed how data is increasing every 2, 3, 4 years. But eventually the loss in the copper, because the copper is not a superconductor, it has finite. And so far, copper is the best. Even, I guess, maybe gold may be better, but copper is as good as you get. But if we run very fast, even copper is giving us a lot of loss. How do we avoid that? One thing every high-speed system uses is called equalization. You can have equalization in one sense. You try the equalization I just showed you here. I placed the pink curve. Its purpose is a high-pass filter, or try to inverse the channel. So that as you see in the middle picture, the channel initially was a blue curve. Finally, it becomes a red curve because I have the pink high pass filter to compensate it. So this is how we use equalization, one type of equalization. And this equalizer can be before the channel, after the channel. Since the whole process is a linear process, it doesn't matter. But that's one equalization. The other equalization is, oh, sorry. The other equalization is, instead of trying to inverse, can we use some training and then use the training to equalize? And it's called, there are many techniques, but we can do that. It's called decision feedback equalizer or similar equalization. So you can train the system when you send one, what the channel, try to corrupt it. And once you understand how a one pulse can be corrupted by the channel, and you can create a training pattern and you can compensate for that. The good thing is you can implement it at transmitter, receiver. And I just want to, if I send a very ideal waveforms, I can also distort it before I send the channel, because I know the channel, I can, and by the time it reaches the channel, it gets very, bad, but if I have another receiver equalization, I can make up for it. So you can do this type of things. Many of the high-speed SerDes nowadays use all types of equalizers at all sides. So for example, this is a realistic scale. I try to scale the waveform. So you can see that if your system has over 35 dB loss, an eye diagram that is shown at the transmitter will be received like the eye diagram you saw on the right for 30 dB loss, quite a significant change. I don't care about the magnitude, but the problem is I don't even know which one is 1 or 0. So I can use equalizer to get it. Maybe I don't want to increase the swing because that requires more power, because the whole idea is to make sure that the ones and zeros are received very well. So we do that type of things. So many of the standard uses this equalization. Not only the high speed, even the memory nowadays, the latest memory uses some type of equalization. I mean, it's very, when I go back and talk to my teachers, when I tell them that memory systems are using equalizer, they get surprised because memory is supposed to be a very damn inexpensive system where we don't need to be this elaborate. But again, we have a lot of transistors on the chip. So transistors are free nowadays. So we can implement a very fancy equalizer. Okay? So equalization may or may not fix all the problems. Actually, to be frank with you, it may not fix a problem, or it may require a lot of power if you want to use equalizer. So one of the way we are doing is, can I run slower, but I can have multiple level of signals? Instead of saying 0, 1, can I have 0, 0, 0, 1, 1, 0, and 0, 0, or 1, 1? So I can have multiple levels of signals and improve the performance of overall systems. And you can take that to even higher levels. You can make a very complex modulation techniques, and you can get a sweet spot for your system to get. And this is also possible. So signal integrity is really, really exciting field at these days. However, to do all these trade-off, we need simulation methods. I have been asked a question about simulation tools. So we need a simulation tools. Unfortunately, to analyze what the pictures I showed you, you need the transmitter and the receiver. And the transmitter by itself can have millions of transistors. And this is analog design. And the receivers can have millions of transistors because I just put some of the key elements in a transmitter and receivers. And you have to form in circuit simulation the way SPICE or any of the SPICE simulation tool, they just represent each transistor by multiple values in a very huge, humongous matrix, which is called modified nodal analysis matrix. And then you have to invert at each time point, as I show on the right. So this is a very expensive process. To complete this analysis, you have to run your SPICE for over a week. So it becomes very, very challenging. So we try not to do a lot often this one. And the problem it is because a channel, remember I told you, it likes to be defined in frequency domain. So if you want to go to time domain, you have to do a lot of approximation. So that makes everything very complicated. And transistors, generally their relationship is defined in time domain. So there is a lot of push and pull, and that makes the computation very complicated. So I think in the early 90s, I think a group of companies representative, they got together and they came up with this IBAS-AMI. The reason was mainly to resolve these simulation challenges, but also it makes it easy that suppliers of a chip do not have to tell the detailed transistor design to external customers. So they can use this algorithmic model as a transmitter and receiver. And as a signal integrity engineer, you consider the package and the board and other connectors with this IBAS-AMI model, which is really a C function. And then you run the simulation. All the simulation tools that are available in the market, they agreed to support this type of modeling approach. So this is one of the major things. Just to show you again, this presentation is not really about IBAS-AMI, but it is an algorithmic model with a lot of C and compiled C, and because we need to make the simulation very, very fast. So this is the way we handle it. So before I go back to answer the question, how do we handle if this signal integrity is so challenging? How do we do? There are three approaches. We can use a statistical or empirical formula where we model not every transistor, but every functions like transmitter, receiver, without going into transistor level models. And you can write a simple MATLAB code or Python code, and you can do, because we want to handle long bit patterns, and to get to a certain bit error rate, this pattern have to be very long. So you can't really do every bit. So you have to use some statistical techniques. So that's most of the time companies or universities built it. And then there is a signal flow. Many of us use Simulink or System View or some other MATLAB type of codes to handle signal integrity work. This is slightly slower, but it gives you more accuracy, maybe from minutes to hours, to do that complicated transmitter and receiver. And if you are brave, you can use the typical Cadence tool or HSPICE or ANSYS tool to do full transistor level and electromagnetic solver. And you can try to minimize because remember, connectors are interconnects are very challenging. So we use a lot of math-based, like order reduction or dimension reduction techniques to make it palatable for the SPICE and transistor level models. So to answer the question, the gentleman on the back, these are the tools that are often used. Again, I'm biased to what I'm familiar in the United States. I'm sure in Europe, there are other equivalent tools, some equivalent tools. I do not include those in this presentation. I think I heard, I don't know what tool was mentioned. I heard that European tools, but for package, we use, I listed them: ANSYS, Cadence, Keysight, Synopsys, Mentor, and CST. Actually, CST is from Europe, I think. At least it was. I guess these companies, they buy each other, so they change every year. And then for chip model extraction, either Redoc and voltage storm, I have, they are very, very, first of all, the investment is very big in this. So for chip side, ANSYS and Cadence and Synopsys in terms of related items. For transmission line, for the things I like, or signal integrity care, there are many tools, but Keysight is one of them, or all of them are there. For system simulation, as I mentioned to you, ultimately we want to solve system. So we use, again, similar tools, and a lot of time we use Python and MATLAB based in-house tools. Okay? Yeah.
Let's say the boundaries very critical, right? So are they group of them doing better than others, or they?
Yeah, you try to tell. I try to be very careful. I don't want to endorse one company from other. I will tell you privately. But yeah, I'm sure. Maybe also it depends on your know-how. I think all tools are getting very close to each other, but I don't want to dismiss your question. There are some tools that are better than others. Yeah, depend what you want to do. If it is RF, high frequency, there are companies that are really out there. If you are interested in on-chip simulation, there aren't that many, and you may want already know. So yeah. So I think I have one more slide to cover. So really, signal integrity, even though it's not, you may not think about it, it's very critical in improving performance, improving cost, because improving reliability of systems. And there is a lot of opportunity because everybody wants to run faster and faster. Why? Because you want your phone to be much nicer, your computer to be faster. So it all already translates into signal integrity. So there is a lot of push in terms of high frequency, and even memory, and all of them are moving. And also, even if you want to do interesting things, there are a lot of challenges, because now, to avoid some of these problems, complex signaling methods, low voltage signaling, that really becomes very, very academic, which used to be academic not long ago. Now it becomes a very common things to do. And then finally, what I want to do is, I just talked about electrical analysis, but thermal and others are equally important. So signal integrity has to take into account, for example, thermal, because anytime the temperature changes, the resistance or the copper value we are using in our analysis will change. So we have to be aware of. So there is a multi-physics phenomena that are becoming very important. With that, I think I finished on time, I guess. So I'm open. I'll open for questions.
Yeah. So I don't work on these interfaces, but I work a lot on RF. I was just wondering, for these standards that you're listed here, is there such a thing called peak to average ratio? And if there is, what are typical peak to average ratios on the signal? Or is that usually not in power that's going to help understand?
No, there is no, because, for example, like earlier that I was asked, what is the receiver, what is the opening that some people design, believe it or not, 15 millivolts, 30. Some standard, they say 100 millivolts is what is required. So it all depends. If it is proprietary, you have all the freedom to do what you want at the transmitter or at the receiver, because that overall aim is really to reduce power. So you can reduce power by making your receiver more sensitive. That way you don't transmit very large swing. I know I don't answer your question, but yeah, it's yeah. Go ahead.
Do you think that in any in the limit, physical limit of service, now we have like one car fee. We think it
Yeah, I tell you.
usually that's something
Yeah, I actually know people who work at 224.
for
Yeah.
the same signal format as
No, it's I showed you maybe 8 palm. That's at least for one paper I see. But the question I thought you were going to when will be optics or photonics or
yeah.
I've been waiting. Yeah, but I think it is about time. But I have said that before, but I don't know. Because remember, economy always decides that, you know, if some clever guy comes with less efficient, less expensive. Yeah. So right now, 224 seems possible, but I don't know enough.
Is that used for like the server to server?
Yes, for server to server. I guess 1 meter distance. I mean, the length is also being reduced. So I think 1 meter is at most you can go. Actually, that is also being reduced a little bit. For say 2 meters, I think by now they must be using some optical links. Yeah.
Like interconnects, you know, some server communicate with fiber.
Yeah, they do. It depends. Yeah, whether you want to communicate from top rack to the border. Yeah, of course they do use. The only problem with that is integrating it with electrical. You know, that the loss and the manufacturing technology and things like that. I mean, there is a company called IR, which seems to be doing well from far away. Maybe I don't know the details, but I'm sure there are other companies that are not disclosing and doing much better. But there are companies, yeah. Yeah. Yes.
Thank you for the opinion for the presentation. I have a question regarding you mentioned about thermal factors. We call impairments to the channel. So are these captured in S parameters, or how do we actually incorporate these? All these variables actually at this moment?
Yeah, right now we are at the early stages. Not long ago, when we do signal integrity, we consider all parameters at room temperature. Now we start taking 60, depending on your application. If it is mainframe, you can go because it's not close to human. But if it is a phone, nobody likes the phone with the cooling system on. So it will be more sensitive to temperature, so we cannot achieve. So right now it's kind of destroying, but it looks like again I'm not praising any rules, but answers or even others are saying that they can run both thermal and electrical together. They can do feedback. Yeah.
So yeah, when you're showing the equalizer function, basically the main idea is you have more flat edges across the process. You're losing no power as a result. And if you do compensate by the on that side, and there are cost benefit analysis there.
Yeah, some of it you know, I think you are considering, the transmitter side, instead of sending one volt, you have to send 2.6 and then you have to use the rest. That you can do, but there are other techniques like decision tree rectifier. You don't use the power for that. So the people use in combination when they run into power limitations or voltage limitation. That's why you have to implement combination at the receiver or transmitter. So the transmitter only, like I said, you will run into it.
So going to the slide number 8.
Okay, sure.
how do we handle, when you look at these plots,
Yeah,
they are,
yeah.
so what are the techniques for something that can be on the channel to see it out or maybe design to see it out?
Yeah. So first, let me decide why do I have a little? This is more. So the reason you have a little is I'm plotting only the interconnect is main problem. So whenever you generate a test dynamic or losses, you have to have some intermediate minus 50 ohm. But the traces, you didn't change that the function of people. That's why. So I guess one way is to, I mean, the impedance of the trace is very different, so you have to get the impedance of the transmitter and receiver very different. Another way is another way, I mean, obviously some of them, like the one chart one, that has a reason because I didn't cover here. Whenever you have a star, you know what, there's something extra handy on the internet. The wave tries to go there, oh, you find it, oh, this star doesn't have anything to do. So it's yeah, so you have to remove that star. And things like it depends on what, but the idea is to have a variety reference between. That's only it's a very challenging problem actually. But
Oh, can you use this as a manufacturing tool where let's say you're making a lot of stuff, you don't have very good quality control? Can you just measure and use it for basic purposes? Pop out things that
yeah, but it's very expensive. It's really difficult.
I know, but my thing is expensive too. So
Yeah.
vendor is making it, they don't know what they're doing.
Yeah.
So maybe you can get in to charge more for one to that piece.
But a lot of times, maybe long time ago, sometimes the company comes to us at the time of the replacement. Hey, this packet is designed with this company and you guys say it's plus minus 15%. This company comes up with plus minus 95%. I want this company to make my device. You know the reason because this one is cheaper. So, what do? We do one of the signal integrity requirements is we want to make sure that the system is designed just to work. You don't want it to work always. For example, I used to work for a company, Xbox, something we used to develop to design something. And the company, the first generation that was out, the company would say, PlayStation, they would say that the whole system and give us each of us. And that system is robust. Anything after that, is, we are told, oh, I have the 200 decoupling capacitors from the board. And you tell me how much I can reduce. Then we take out each of them until it barely works. So yeah, what you said is true because eventually you have to make profit. I mean, I don't blame the manufacturer, company why they do that. It makes sense. You just want to make barely works and meet the requirements. Obviously, now it doesn't have much conflict.
There is a limit where the equalizer will be impossible to design an equalizer. For instance, if your channel looks like this, if you look at the green trace, you're at 0 dB at low frequency, you're at 60 dB at 25 meter. That's almost like a factor of 1,000.
Voltage. So
if you look at
yeah, you can.
Yeah,
That's why I guess I'm sure you got the point. That's why we don't want to run very fast. Actually, there is an answer for your question already in my slides. Because that's even if you can make it, it's very power efficient. Okay, so where is it? Well, I think I can use this picture.
you know, instead of going all the way here, I can use different modulation techniques. Every time I have multiple eyes, the frequency is shifting to the left. That's why it's the advantage.
Okay, so recently there have been, not really recently, probably past year ago, there's a lot of talk about using machine learning to predict the eye, the PI analysis. Do you see value in that and how it helps?
Yeah. If you do it correctly, I'm sure it will. Because there are few examples. Sometimes, you know, because the whole idea of machine learning is to capture the hidden pattern in the data. So yeah, it has value, but the way it's being used in SIPI is kind of shaky right now. But I'm sure after a few papers, people will become experts. But I do not think it's good. Yeah, if it can capture hidden feature of your system, including the resource and everything, why don't you use it? Yeah, sure. And I think there is a hope, but right now there are many noisy papers. And we just have to be careful. Yes.
To avoid people stealing your stuff, people will embed circuit elements that are not really there. You just want it so that they can check that it's stealing your stuff. Right?
Yeah.
So does that affect stability and
In terms of sneaking the data? Yeah, this is another reason in production, but there are techniques to solve that type of. Yeah, and on the other hand, at least there are clear ways of so one thing is, if I just look at a pattern, I can tell a lot about what you are doing. This type of thing. Yeah, there are possibilities, and you can, there are companies which sell encryption, if you embed that in your chip, people cannot see the it's already, yeah. Okay. Thank you very much for the